In this video, I will introduce you to a new integration tool called Integration by Parts. This is a BC-only topic. First, let's talk about when we will need to use integration by parts and when it will be easier to use the tools that we already know. You will try integration by parts when, number one, you are integrating a product, and number two, U substitution doesn't work. Do we need integration by parts to integrate this first example? Well, we are integrating a product. So the question is, does normal U substitution work? Well, let's try if we let U equal x squared, then U prime is going to equal 2x. When you do the substitution, you get this, and instead of dx, you write du over u prime, so du over 2x. Then we notice that the x in the denominator cancels out the x in the original integrand, and that's what we need to be able to solve this problem by U substitution. So we don't need any new method. We can use the old tools that we already know. What about this example? It looks very similar. We are integrating a product, but what about U substitution? If we let u equal 2x, then u prime is going to equal 2. When we do the substitution, we get this, and then instead of dx, we write du over u prime. But there's nothing to cancel out the x from the integrand, so we're stuck. This is why we will need something new. This is when we would try integration by parts. This next example is not written as a product, but if we end up needing to use integration by parts, it would be easy to rewrite this as x to the negative 1 power times the natural log of x. So we can write this as a product, but do we need to? What about regular U substitution? If we let u equal the natural log of x, then u prime is going to equal 1 over x. When we do the substitution, we get this, and then we rewrite dx as du over u prime. And then we see that the x from the integrand is canceled out by the 1 over x. That's what we needed to be able to solve this problem. So we will not need any new methods. We can solve this by the old tools that we already know. What if we try something similar on the last example? We are integrating a product, but will regular U substitution work? If we let u equal to natural log x like we did last time, again, u prime is going to equal 1 over x. When you do the substitution, you get this, and then you replace the dx with du over u prime. But x will not be canceled out by this 1 over x. Dividing by 1 over x is the same as multiplying by x. So this would be the same thing as having x times x, which would be x squared. Because the x from the integrand does not cancel out, we would be stuck, and we will need a new method. This is when we would use integration by parts. Here is the integration by parts formula. Write this down in your notes, put it on a flashcard, and memorize this. I'm going to spend the rest of this video teaching you how to use it. Let's use integration by parts to integrate this product. Step 1 is to choose what part of this expression will be u and what part will be dv. Later in the video, I will explain more about how to choose wisely. But for now, let's split the expression right here. So we will let u equal x, and we will let dv equal e to the 2x dx. Step 2 is to find du and v. We can find du by taking the derivative of both sides of this equation. The derivative of u is du dx, and the derivative of x is 1. Multiplying both sides of the equation by dx gives us du equals dx. So we found du, now we just need to find v. We can find v by integrating both sides of this equation. The antiderivative of dv is v. On the right side, we need to do a little mental u substitution. If u is 2x, then u prime is 2. We end up dividing by u prime. So we need to divide by 2 by putting a 1/2 in the front. We are left with the antiderivative of e to the u, which is e to the u. We save the plus c until the very end of the problem. Don't worry about it right now. We don't normally show this middle step, so I'm going to go ahead and erase that. So at this point we have found du and v. Step 3 is to substitute for the expressions in the integration by parts formula, which I've rewritten here. Notice that the black part represents the original problem, while the light blue part represents the solution that we need to set up. Before we do that, let me mention a couple of things that I use to help me remember the formula. First of all, notice that the left part and the right part are sort of backwards. Listen for the uv and then the vu. uv minus the integral of v du. You hear how they're kind of backwards? So that helps me remember. The other thing is that the setup follows a sort of zigzag pattern. First we need to write u times v. So we're going to multiply this times this. In other words, x times 1/2 e to the 2x. For aesthetic reasons, I'm going to put the 1/2 out in the front. Next, we need to write minus the integral of v du. So that's this times this. In other words, 1/2 e to the 2x times dx. When I write an integral, I like to put the constant out front, so we have this. The last step is to integrate the remaining integral. Hopefully, this is something we can integrate using the tools that we already know. To integrate e to the 2x, we need to do a mental u substitution. So if u is 2x, u prime is 2. We end up dividing by u prime. We can show that we are dividing by 2 by putting a 1/2 out in the front. Then the integral of e to the u is e to the u. And now we will put the plus c. Of course, 1/2 times 1/2 is 1/4. So this is the final answer. Let's go back to step 1 for a minute. How do you choose which part is u and which part is dv? Number 1, start with u. And number 2, follow LIATE. LIATE is an acronym that stands for logarithmic, inverse trig, algebraic, trigonometric, and exponential. How to choose the best u sounds like the title of a self-help book, but LIATE ranks the types of expressions in order from the best u to the worst u. So if you see a logarithmic expression, let that be u. Otherwise, move on to inverse trig. If you don't see either one, look for an algebraic expression, a polynomial, to be u. If you don't see any of those, look for a trigonometric. Finally, if none of those are present, then I guess you're stuck with exponential, but that's the worst, because if you take the derivative of an exponential function, it doesn't change. The derivative of e to the u is still e to the u. So that's why this is at the bottom of the list. You don't really get anywhere. Let's try this example. The first factor is algebraic, because x is a very simple polynomial. The second factor is clearly logarithmic. So according to LIATE, the logarithmic factor is the best choice for u. So u is natural log x. That means dv is everything else. So dv is equal to x dx. The next step is to take the derivative of the u expression and take the integral of the v expression. So, taking the derivative of both sides, we have du dx is equal to 1 over x. But we really just want du on the left. So multiplying both sides by dx, we get du equals 1 over x dx. And next time we will just go straight to this. Now we integrate the dv expression. The antiderivative of dv is just v. And the antiderivative of x is 1/2 x squared. Don't worry about the plus c. Next, we need to fill in the blue part of the integration by parts formula. We can do that easily by following a zigzag pattern. U times v is this times this. Natural log x times 1/2 x squared. For aesthetic reasons, I prefer to write it the other way around. Next, we write minus the integral of v du. So minus the integral of this times this. So 1/2 x squared times 1 over x dx. I like to put the constant out in front of the integral, and x squared divided by x is just x. The antiderivative of x is 1/2 x squared plus c. On the last step, we can multiply 1/2 times 1/2 and write 1/4. So this is the final answer. Let's try another example. In this case, both factors are algebraic, so Liate will not help us choose the best u. In a case like this, I would first try letting u be the simpler one, x. If this doesn't work out, we can always go back and let u be the other one. For now, let's let u equal x. That means dv will equal everything else, the square root of x plus 1 dx. Taking the derivative of both sides of this equation gives us du equals dx. One more time, what really is happening is that on the left side we have du dx, and on the right side we have 1. Then we multiply both sides by dx, and that gives us du is equal to dx. But we're just going to go straight from here to here. The square root of x plus 1 is the same thing as x plus 1 to the 1/2 power. I'm going to think of it this way to make it easier to integrate. The antiderivative of dv is just v. To find the antiderivative of x plus 1 to the 1/2 power, I need to add 1 to this exponent, which gives me 3 over 2. Then I need to divide by my new exponent. Dividing by 3 over 2 is the same as multiplying by 2 over 3. I should acknowledge that technically I just did a mental u substitution, where u is x plus 1. We then need to divide by u prime, but u prime would be 1, so it changes nothing. Next, we need to follow the zigzag pattern to fill in the right-hand side of the integration by parts formula. We start by writing u times v, so that's this times this. So here's my u times v. Next, I need to do minus the integral of v du. So that's minus the integral of this times this. Putting the 2/3 out in front of the integral, we have this. We can integrate x plus 1 to the 3/2 power using a mental u substitution. To integrate u to the 3/2 power, we have to add 1 to this exponent. So that's going to give us x plus 1 to the 5/2 power. Then we have to divide by the new exponent, but dividing by 5 over 2 is the same as multiplying by 2/5. When we do a mental u substitution, we have to divide by u prime, but in this case u prime is just 1, so it changes nothing. So this is the final answer. Sometimes you have to do the integration by parts more than once. On this example, I'll show you how to handle that. But first we need to pick the best u. The first factor is algebraic, while the second factor is trigonometric. Algebraic is better than trigonometric, so let's let u equal x squared. That means dv is sine x dx. Taking the derivative of both sides gives us du is equal to 2x dx. Integrating both sides gives us v equals negative cosine x. Now it's time to fill in the right-hand side of the integration by parts formula, following this zigzag pattern. U times v is this times this, so that's negative x squared cosine x. Then we have minus the integral of, so minus, and I'm going to switch colors here and put the integral of v du. That's going to be this times this. Notice there's a negative in there. That's going to come out front and turn this into a positive. So I'm left with 2x times cosine x dx. Unfortunately, this red integral is still not something that we can find using u substitution, so we are going to have to do integration by parts again. This time around, let's let u equal 2x, which means that dv will equal cosine x dx. Taking the derivative of both sides, we have du is equal to 2 dx. Integrating both sides, we get v is equal to sine x. We bring down the first term, and then we need to find the antiderivative by filling in the right side of the integration by parts formula. U times v is this times this, so we have 2x sine x. Then we have minus the integral of v du. That's this times this, which I will write as 2 sine x dx. This is something we can integrate. Let's bring out the 2, and the antiderivative of sine is negative cosine. The negative is going to turn this minus to a plus, and we have plus 2 cosine x plus c. So this is the final answer. That procedure was a little bit long, so luckily there is a shortcut that we can often use to make this go a lot faster. The shortcut is called the table method, and we can use this when taking the derivative of u will eventually become 0. You start off the same way by stating what your u is and what your dv is, but then just go ahead and take the derivative of your u over and over again until it becomes 0. So the derivative of x squared is 2x, and then the derivative of 2x is 2, and the derivative of 2 is 0. Moving over to the dv, we are going to integrate repeatedly. The antiderivative of sine is negative cosine. Bringing down that negative sign, the antiderivative of cosine is sine. We bring down the negative sign again, but the antiderivative of sine is negative cosine, but the negative turns this minus to a plus. From here, we can go directly to the answer by multiplying each of these diagonals and adding up the products. With one small modification. For the first product, we keep the sign whatever it is. For the second product, we change the sign, and for the third product, again, we keep the sign whatever it is. So when we multiply x squared times negative cosine x, that is going to give us negative x squared cosine x. And we keep that sign. If we multiply 2x times negative sine x, that would give us negative 2x sine x. But we switch the sign and make it plus. And then we multiply 2x times cosine x, so we get plus 2 cosine x. And we keep the sign. And don't forget the constant of integration plus c. And that's the final answer. Wasn't that fun? Much faster than doing it the long way by hand. Let's practice the table method again on this example. The first factor is algebraic, and the second factor is exponential. Algebraic is better than exponential, so let's let u equal x to the third power. We can see why the table method is probably going to work, because if we take the derivative of x to the third power over and over again, it will eventually become 0. If u is x to the third power, then dv is e to the 3x dx. Let's take the derivative over and over again until we get 0. The derivative of x to the third power is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6. And the derivative of 6 is 0. The antiderivative of e to the 3x will require a little mental u substitution. If u is 3x, then u prime is 3. When we do the antiderivative, we divide by u prime. So we have to divide by 3. So I put a 1/3 in the front. Then the antiderivative of e to the u is e to the u. If I take the antiderivative again, I keep the 1/3 that's in the front, and because of the mental u sub, I'm going to have another 1/3, and the antiderivative is still e to the u. Of course, we will write this as 1/9. When we take the antiderivative again, we start by bringing down the 1/9. Because of the mental u substitution, we will have a 1/3 in the front, and the antiderivative is still e to the u. We will write 1/27. One more time, bring down the 1/27, and because of the mental u substitution, we end up dividing by 3, and the antiderivative of e to the 3x is e to the 3x. The 1/27 times 1/3 became 1/81. From here, we can write the final answer by finding the products of each of these diagonals and adding them up, with the exception that we have to be careful about the signs. We will keep the first sign, change the second, keep the third, change the fourth. Sometimes instead of writing keep, change, I will put a plus to show that we are multiplying by +1, and I'll put a minus to show that we are changing the signs by multiplying by -1. It's just easier to write plus, minus, plus, minus, rather than keep, switch, keep, switch. So we can write the answer now. X to the third power times 1/3 e to the 3x gives us 1/3 x to the third power e to the 3x. And that's a positive multiplier, so we just keep it the same. On this next one, we have 3x squared times 1/9 e to the 3x. 3 times 1/9 is 1/3. And then we have x squared e to the 3x. But this one, we're going to change the sign by multiplying by this negative. So it'll be a minus. On the next one, we have 6 times 1/27. That's 6/27, which reduces down to 2/9. And then we have x times e to the 3x. This one, we keep the sign the same. And then for the last product, we have 6 over 81, which reduces down to 2 over 27. And e to the 3x. But this one we changed the sign, so it'll be minus. And don't forget the constant of integration. I think you will agree that you would not want to do this problem by hand. We do not know a rule for the integral of natural log x, but we can use integration by parts to find this single term integral. All you have to do is think of it as the integral of natural log x times 1. So we have a logarithmic expression times an algebraic expression. Logarithmic is better than algebraic, so let's let u equal the natural log of x. That means dv will equal 1 dx. Taking the derivative of both sides gives us du is equal to 1 over x dx. Integrating both sides, we get v is equal to x. Now we set up the integration by parts formula. U times v is natural log x times x, which I will write as x natural log x. And then we put minus the integral of v du. So that's x times 1 over x dx. Of course, x times 1 over x is just 1, so now we have this. And the antiderivative of 1 is x plus c, so this is the final answer. Here is another single-term integral that we can find using integration by parts. All we have to do is think of this as arctangent x times 1. So we have an inverse trig factor and an algebraic factor. Inverse trig is better than algebraic for u. So let's let u equal arctangent x. That means dv is 1 dx. Taking the derivative of both sides gives us du is equal to 1 over x squared plus 1 dx. Taking the antiderivative of both sides, we get v is equal to x. Now we fill in the integration by parts formula, starting with u times v, which is this times this. Then we do minus the integral of v du, so that's this times this. We can find this integral using u substitution. Let's let u equal x squared plus 1, so u prime will be 2x. Performing that substitution, we have x over u, and then instead of dx, we write du over u prime. In other words, du over 2x. But then we notice that the x's cancel each other out. This 2 ends up as a 1/2 out in the front, and then we just have the integral of 1 over u, which is the natural log of the absolute value of u plus c. Substituting x squared plus 1 back in for u gives us the final answer. Notice that because x squared plus 1 is always positive, we don't need the absolute value symbols anymore. Be emotionally prepared because this one is going to be next level. We notice that we have an exponential factor and a trigonometric factor, both of which are bad choices for u, but trigonometric is a little bit better than exponential, so let's let u equal cosine x. That means dv is e to the 2x dx. Taking the derivative of both sides gives us du is equal to negative sine x dx. Integrating both sides, we get v equals, and here comes a little mental u substitution. If u is 2x, then u prime is 2. We must divide by u prime by putting a 1/2 in the front. the integral of e to the u is e to the u. Time to set up the integration by parts formula, starting with u times v, which is this times this. Then we do minus the integral of v du. So that's minus the integral of this times this. I went ahead and put the 1/2 out in the front. Be careful, we have a negative sine x. I'm going to put that negative sign out in the front, but that's going to change the minus to a plus. But here we run into a problem, because this integral does not look any easier to solve than the original integral. So let's try doing integration by parts again and see what happens. Just like before, we will let u equal the trig part and dv will equal the exponential part. Taking the derivative of both sides, we get du is equal to cosine x dx. Integrating both sides by mental u substitution gives us v equals 1/2 e to the 2x. Picking up where we left off, I have brought down the first term and even the plus 1/2, but now I need to emphasize a common mistake that I want you to avoid. When we do integration by parts, we get two terms. For that reason, when there's a number in front or even just a negative sign, we have to put the integration by parts inside brackets or parentheses. That's because eventually we will have to distribute the 1/2. Setting up the integration by parts formula, we start with u times v. So that's 1/2 e to the 2x times sine x. And then we do minus the integral of this times this. So now we have this. Let's go ahead and distribute the 1/2. So now we have this. At first we are very sad because we once again get this integral that is no easier to solve than the original integral was. But here's where the trick happens. Remember, everything we've done is supposed to be the value of the original integral. So let's set this entire expression equal to the original integral. When you set what we have so far equal to the original integral, do you notice anything interesting? The original integral appears in the expression that we just found right here. That means these two terms are actually like terms. We can put them together by adding 1/4 integral e to the 2x cosine x dx to both sides of the equation. When we add these like terms together, we get this. If it helps, think of this as 4/4 times the integral. So 4/4 plus 1/4 is 5/4. This is the original integral we were trying to find. So to finish off the problem, all we have to do is get this by itself. To get rid of the 5/4, we can just multiply both sides of the equation by the reciprocal, 4/5. So we see that the original integral is equal to this. Just add a plus c on the end, and that's your final answer. I told you it was going to be next level.